The idea when we decided to co-locate the conferences, so welcome to everyone. The right thing to do now is not to listen to me. Instead, please go and complete the survey that Ken asked us all to complete prior to his talk. And that's a bit.ly up there. If you've done that, now you're allowed to listen to me. So it's really a great pleasure to introduce Ken Koedinger from Carnegie Mellon University. A very long list of achievement for Ken. So Ken, please add the ones I'm missing. So professor of human-computer interaction and psychology with a background in math and computer science from Wisconsin, and then PhD in psychology with John Anderson at CMU. Roughly 250 peer-reviewed papers. I wasn't sure what's the updated number. 17,000 citations and an H-index of 60, which is really nice. Now Ken has, aside from developing the Cognitive Tutor, he's really the person who took the Cognitive Tutor platform into the classroom, platform that now has nearly 500,000 learners a year, as we heard Steve Reeder talk about earlier. And that's learning at scale before we had the term, right? 97 was, I think, the paper, the big city paper about cognitive tutors in the classroom. And there was a lot of vision there, and as well in other things done. Ken also really likes to bring people together as the co-founder and director of the Pittsburgh Science of Learning Center, co-founder of Carnegie Learning, founder and initial director of Master in Educational Technology and Applied Learning Science program at CMU. And to me, that's another example of learning at scale. This time, it's learning for us, the community, by bringing us together. Other maybe more dubious achievements. Ken made it to the Pittsburgh 40 under 40 list. And I will not tell you what year this was, so you cannot extrapolate the 40.
It's a long time ago.
Not that long. Ken was another so-so achievement. He was my advisor. And maybe the most...
The hardest but the best thing I've ever done.
But maybe the best one, actually, is he had real, actual penguins running around in his wedding. So yes, and maybe I'll finish with two things that I learned from Ken. One is to always doubt, and that's really impressive. Ken is also really good at doubting himself. He usually will smile and then ask, really? So whenever I see Ken smiling, I know I'm in big trouble. And the other thing is that the student is not like me. I think that's another lesson that repeats often. And there is some zen in this statement. Because if the student is not like me, then what is the student? And probably the student is also not like other students. So we do need adaptivity. We need rigor in how we study students. Like there's a lot of follow-up from this statement. So I'm very curious to see what I'm going to learn today. So thanks for coming, and please join me in welcoming Ken.
Thanks, Ido, for that wonderful introduction. Actually, I've sometimes experimented with the follow-up to the student is not like me, which is I am not like me. That's an open-ended question. Interpret that. See if you can figure out what that means. Thanks to all of you who have done this survey, and just to show live data collection in action, and or to expose my poor technology skills. Let me see if look at that, got it. We have 103 responses, up 50% from the last time I looked. As you listen to a lecture, let's see, can I get my mouse over here? Do you know when you are learning and when you're not? 66% say they know. As you give a lecture, do you know when your students are learning? 83% say they don't know. To effectively and efficiently redesign a course that produces better student outcomes, one should apply learning science is the most popular response. Follow your intuition's least popular. Does answering an in-video question correctly mean the student has learned the associated concept or skill? 85% say no. I have a corresponding survey at the end. So we'll see if anything changes. I believe in learn by doing. So that's your pre-assessment. And let me fire up the PowerPoint now if I can. Oh. I gotta find my mouse again. It's over there, it's over here. There it is. So I want to talk about learning research that makes a difference in educational practice at scale. And before I do that, and I guess in line with Ido's comment about my wedding with the penguins, another consequence of that wedding is my two daughters, Sasha and Lisa. And I add these here just to remind ourselves that learning and education is a highly personal thing, and I think a lot of why we're all in this is because we want to make a difference for the students of the world, not just children, but adult learners as well, and I'm certainly committed to that. Here's my preview of my overall argument. Strategy, talk strategy. I actually learned from Vincent to tell you what I'm going to tell you ahead of time here. So the first point I want to make is that you cannot see learning, that you should beware of illusions of learning. If you're a student, you might think, for example, that you're learning from a lecture, and you may or may not be right. I'll show you a little bit of relevant data. Instructors watching students, I guess many of you are convinced that you can't tell from watching your students whether they're learning. But what do we do if we can't rely on our self-reflections? Data is a huge opportunity, as we all know. Students need data, they need formative assessment feedback, and instructors need data too. And they need that data not only to adapt their instruction to their students in their class, but also to improve the design of their instruction. So as we take this idea of using data and try to scale it up for practical learning science, I want to articulate two big challenges. One is essentially domain-specific and one's domain-general. The domain-specific challenge is that we don't really know what we know. Experts are only consciously aware of about 30% of what they know. And another challenge I'll elaborate is that the design space for different ways to support learning is absolutely huge on one hand, and there's not very good evidence that what we learn in one domain transfers to other domains, so one size does not fit all. I think these challenges are actually opportunities on the other hand, and we're at a point where education, science, and technology can be really revolutionary. And I mean that not just through spreading access and personalizing instruction through technology, but I think this notion that technologies can provide us with data to drive iterative improvement is super important. And you know, I think I agree with Mike that we know a lot, but my sense, I like this metaphor that we're maybe at the Model T stage in terms of applying science and technology, and we could have jet airplanes of education going forward by pushing the science farther and pushing applications of it. I am a big fan of data, so you might say data rules, but what I really want to emphasize is iterating on that data through gaining insights from it, so not just black box machine learning, but really understanding what your data and your models of your data tell you and improving from there. So I'll say a little bit about what I think we know and don't know, and then go from there to build up a case for how we can scale learning science through practice, through building social technical infrastructures that support iterative engineering and practice-relevant theory. I'll give you some examples of scaling deep content analytics and scaling iterative course improvement. So let me start with learning science knowns and unknowns. And if you're keeping track of the pre-assessment, this is relevant to some of those questions. So do students know when they are learning, and can we see it? I think the simple answer to this is no. We experience lots of illusions of knowing and learning. There are many results along the lines of suggesting that students are pretty poor at judging what they learned. One way to evaluate this is whether students can predict after experiencing some learning event how well they will do on a follow-up assessment. And those kinds of predictions lead to pretty low correlations. Focusing on the second reference here, here's some display of data from this study where they gave students excerpts about baseball and multiple excerpts, and following each they had to answer a set of questions. But before they answered those questions, they had to predict after the reading how well they were going to do in answering those questions. And the y-axis here are the correlations for individual students, and you see they're all over the place, right? From perfectly non-correlated at -1 here up to 1. And if you said when you listen to a lecture you know when you're learning, maybe you're one of these folks up here, but I would suggest that you may be in the minority in that regard. That overall the correlation is just a little bit over 0 here for this kind of prediction. What the x-axis here shows is that this ability to predict how much you're learning is not associated with expertise, at least not in this data set. And there's some debate in the literature about that. But the overall point is that it is hard for students to do this. And furthermore, when you ask students, as we often do in higher ed, what they think of a course, that's important. We want them to like it. But does that correlate with what they're actually learning? And the evidence there is not good. The correlations are quite low. I would submit, I don't know the literature what literature there is on this so much, but there are certainly relevant efforts to look at how observations, say, of student facial expressions can be used to predict downstream learning outcomes. And there are some reasonably reliable such predictions, but they're not always in obvious directions. So confusion, if you look at your class and they look confused, you might think, oh, I'm not doing a good job, but often confusion is a good thing for long-term learning. So that's hard too. And certainly, why is this so hard? Well, novices are already kind of strapped to learn the content in their domain, so they're using their mental resources to a great extent to learn. But if we're asking them, to monitor their learning, that's a bigger demand. But monitor it relative to what? Since they're not experts, they can't really compare what they think they're learning against what they should be learning. So turning more generally to what we know about what works in supporting learning, we heard some nice things about that from Mike this morning, and I'll just give a little bit of another view on some of those same issues. I think in general, if you listen to the public dialogue, it often sounds as if there's just two ways to learn, and they tend to have these kind of basics versus understanding distinctions. But, the learning science research has really elaborated many more dimensions, and there are lots of sources like these two books and others that have given us indication of progress. Visual learning, which Mike mentioned, is yet another one of these books. But just to review some of these, there's lots of work that spaced practice is better than massed practice for long-term retention. We just heard an example in one of the previous sessions about this. But it is the case that there are circumstances when massed practice is sometimes better. This next one I'm going to elaborate a bit later, so I'll skip it for now. There's somewhat conflicting research on direct instruction versus discovery learning, showing positive results for direct instruction under some contexts, but other contexts emphasizing active learning over lecture. There are many other debates. Having students do the explaining rather than the instructor is powerful. Mickey Chi, amongst others, has shown that. But there are some cases, as Joseph Williams has shown, that where asking students to explain actually hurts their learning in some contexts. Similar results on interleaving versus blocking. And a lot of these come down to differences in whether you want to emphasize instructional forms of assistance that reduce cognitive load for students, and so that's on the more support side, versus forms of learning support that might reduce assistance to help students put students in situations that might be more difficult for them, but in which they can construct their own knowledge. And Vincent and I wrote about this notion in terms of an assistance dilemma in a paper a number of years back. These are individual dimensions, but if we think about designing instruction, we need to think about combining all of these, and that's where it gets really hairy. So let's just think about how big the design space for learning supports is. So I've organized each of these dimensions roughly on this more assistance versus less assistance or more challenge. So here again is massed or focused practice versus spaced or distributed practice. And one thing to note on all these dimensions, although the research often just compares two different conditions, there's also often a whole spectrum of possibilities, like gradually widen. And there are other dimensions, like how much should you have students study examples versus practice on problems, or should you mix it? And these dimensions combine. So unlike the debates about education in the popular press, we're up to not 2 options, but 9 options. But that's just 2 dimensions. And in this paper, reviewing a number of these different books and sources, we articulated 30 different dimensions. And when you start combining them together, right, like whether the examples or problems are more concrete or more abstract, whether the feedback you give students is more immediate versus more delayed, whether you block topics in chapters or interleave them, whether you do the explaining or whether you ask students to explain, these start to blossom into a pretty complex space. And I've only included a subset of the 30 that we came up with. But if you consider all these options, and also the fact that there's lots of research that suggests that what works for novice learners often is different than what works for more advanced learners, the design space is way more than 2 options. It's like 200 trillion different ways to teach. So there's a challenge for us. Now, there might be an easy way out if on each of these 30 dimensions we get the same answer for every course context in which we apply it. So that would be great. Then we could just apply learning science. You might recognize that as one of the options, right? So our first question is, how do we get there? How do we run enough experiments cross courses? That's really important, because I think we're often, the psychologists are often sort of obsessed with internal validity of their studies, but don't do a lot to see whether they extend to new contexts. When we do that, do we get consistent results? So Ido mentioned the cognitive tutor work, and I wanted to sort of set the stage for some of the technologies that we've had the opportunity to explore a lot of these dimensions in the context of not just cognitive tutors, but other environments like them. But just to give you a little bit of a sense for the adaptive support for learning by doing that are in cognitive tutors, here's a problem-solving activity, a sort of mini project in the middle of the algebra course, where a typical problem like this has students analyzing some authentic problem situation, like which of these 2 cell phone plans should you use given the monthly per minute charges and the fixed monthly charge, and under what circumstances, and use table and graphical and symbolic models, representations to build models of the situation that can help you answer not just one question, but multiple questions about this problem scenario. And as students work through this, there's this intelligent tutoring system fueled by a cognitive psychology researcher or a cognitive tutor that's tracking each move, and not just the individual moves, but the plan as it's unfolding, such that the context matters, that this response, which involves a variable t, is dependent on previous answers this particular student made. So the system has to be smart enough to track those kinds of dependencies. And then can notice, for example, here the students forgot the fixed cost in entering this formula, and there's an available feedback message that points that out. So that's one form of instruction. They're asked challenging questions, like here this one's about what's the crossover or the break-even point here. And if they need, they can ask for help that provide context-specific instruction to students just when they need that. So the student, by asking for help, has essentially said, this is a place where I think I could use some instruction. And furthermore, when they do this or make an error as in above, the system's updating a model of what they do and don't know, and tracking that, giving students feedback on it, but importantly also then individualizing the future instruction for students to help them acquire the concepts and skills that they need to acquire. So lots of evaluations over many years since that big city paper that Ido mentioned, and that was a study in the early 90s. Steve Ritter mentioned, I think it was yesterday, this recent study of about 149 schools that showed in the second year of implementation essentially a doubling over the school year of student achievement as a consequence of using the full cognitive tutor course, not just the technology, but the text and teacher professional development materials that are part of the course. Over these years, we also started to take these ideas and incorporate them in college-level online courses, so this is an open learning initiative, and reaching some pretty good scale from about 30 first-year college courses. And one of the best demonstrations of that is a study that Marcia Lovett and others did, comparing a traditional introductory statistics course taught by a great Carnegie Mellon instructor with smart students, in contrast compared to a blended version of the course that used the open learning initiative materials as well as an instructor, but was taught in half a semester, so 9 weeks instead of 18 weeks. And the outcomes were assessed on an assessment that's sort of the statistics analog of the force concept inventory in physics. They have a test called CHAOS. I think it's concept assessment in statistics. On that test, the traditional course produced a 3% pre to post gain, whereas this blended course in half a semester produced an 18% gain. So pretty powerful demonstration of this kind of built-in additivity and data-driven design of a course. So with these kind of technologies, though, that big space I presented earlier, there's an opportunity to use them to do what have now been called A/B tests in industry. But we started doing this a number of years ago, even before we started this center. But in 2004, we were lucky enough to get one of 6 science of learning centers in Pittsburgh. And over the last 10 years or so, we've had a substantial amount of funding for that center. And we've really committed to this idea of using these educational technologies that are in wide use, not just cognitive tutors and OLI courses, but also some language learning online courses and materials, some educational games, using them to do basic research in the context of those functioning courses. And we built a kind of social infrastructure to get researchers like psychologists and educational psychologists out of their labs to run studies in the context of these courses. And we ran over the 10-year period more than 360 of these kinds of studies and have accumulated data from these studies and others now in this data shop resource. Last I looked, there was over 820 such data. So I wanted to show you a bit about what we learned from these in vivo experiments here and reflect on this question of whether one size fits all. So this is a table from our CLE framework, the Knowledge, Learning, and Instruction Framework paper in Cognitive Science a few years back, where we had started to reflect on how different studies here shown in these cells that are addressing different content domains, when have they been successful? So in other words, when we implemented an optimal scheduling program that gradually widened practice, did it help students in learning Chinese vocabulary? And indeed it did in this study. And what I particularly want to focus on is how some of these rows where we've explored principles, instructional principles across domains, they're not all plus signs, like this one. And what we came to believe and articulate in this framework is how there are really different kinds of instructional goals and that what works depends on those knowledge goals. Ideal instruction depends on the knowledge goals. And furthermore, we can elaborate that by trying to understand what are the learning processes at play. This happens because different learning processes are at work for these different kinds of knowledge. And in particular, we see this association, essentially, that suggests that if your goal, like in learning Chinese vocabulary, is essentially about learning facts, then memory processes are critical, and instructional supports that encourage memory will be best for those. But to the extent that the goals involve inducing some general rule or skill across multiple contexts, then you need learning processes that do some kind of induction and perhaps refinement with practice and negative examples. And so we see a positive here. And then if the knowledge involves deeper understanding and rationales, then you really want students engaging in understanding and sense-making, and things like we heard in the keynote yesterday that support students in collaborative dialogue can be quite powerful. But these things don't work if they're misapplied to contexts. Having a long classroom discussion about why the Chinese word for teacher is Lao Shi is probably not going to be very productive. And we've in fact observed this. And what the framework purports to help us understand is why we see inconsistencies, especially when we look across the different disciplines of the learning sciences. So there's psychologists contributing ideas, educational psychologies, folks in schools of eds like math educators, and they often are coming up with competing recommendations. And I think it's not just limited data, it's often that they're focusing on different goals and therefore coming to different conclusions, because those different conclusions indeed are right once they're appropriately conditionalized. So just to delve into this row a little bit, I've labeled it worked examples, but you could flip the pluses and minuses and call this row the testing effect, and I want to show how that works out. So one of these documents that summarizes recommendations is this practice guide from the US Department of Education. I was on this panel in 2007, and one of these recommendations is essentially about practice, retrieval practice, or the testing effect. Use quizzing to promote learning. And another one of the recommendations that was here is this worked example principle. And I had a funny feeling at the time, but it took me a few years to really sort of start to think, boy, did we say two opposite things in this guide? So let me say more about that. So the testing effect, there's lots of psychology research, and this is more cognitive psychology than ed-psych in this area. Tests enhance later retention more than additional study of the material. Contrasting with a lot of educational psychologists who have suggested that, in fact, we often do too much practice and not enough study of worked examples. And they, in one of these papers, which generated a lot of controversy, has this quote: "A worked example constitutes the epitome of strongly guided instruction," and good instruction from their point of view. And theoretically, there are really two different stories here. Both have some plausibility to them. The testing effect folks say this is an instance of a general phenomena, which are sometimes during the learning process, it's good to have it be harder. And those, while for students, this is one of those things that produces illusions. It feels like they're not making progress. For example, in spaced practice, they fail more often, right? And if you ask them which is better, they say mass practice is better because it feels like they're learning more. But often, these desirable difficulties indeed produce better long-term results. Conversely, the argument for worked examples is that that if you give students practice prematurely, that they will flounder, they'll have too much extraneous cognitive load, they'll produce misconceptions, and they need more guidance. So what's right and what's the mechanism, and how, are these two things really contradictory? So to give a sense for the similarity, consider a typical kind of content in a testing effect study, which would be essentially to learn like a paired associate like this, that this Chinese word in the pinyin notation means teacher. A study trial is to study this combination where you have both the input or the prompt and the answer. And a test trial is you just have the prompt. And in studies, in experiments on the testing effect, a typical thing is to give, say, something like 3 study trials and then a test trial where they have to retrieve what Laoshi is in English. Or 1 study trial followed by 3 tests. And importantly, in most of these studies, these test trials have feedback after them. So there's some opportunity, if you don't get it in the test, to still get it right. And one typical result here is that on a long-term retention test, you get better outcomes from this procedure that emphasizes more testing or more practice. So in contrast, and here's an example from a worked example study where the examples are, here is solving a literal equation for A, and these are the steps. That's the worked example. And here is a problem where the student has to fill in this. So you might notice, I hope you notice the similarity. You know, this we're giving A and B, here we're giving A and asking for B. But maybe there's some differences here that you might notice also. But the typical results here flip-flop. The designs are sometimes subtly different, like here a study and an example are analogous. So a typical design here is half examples and half problems or tests, whereas this is all problems or all tests. And the outcomes are flip-flopped. So what's going on here? Well, one thing we wondered is maybe in these studies that were done mostly on paper, the problem-solving conditions indeed do not provide enough guidance. And if in an online environment there was more guidance provided, maybe the worked example effect wouldn't appear. So that basically the argument is that in the context of an online tutoring system, this step-by-step support might make the cognitive load low enough that the worked examples are unnecessary. So we did a number of studies across various domains. Let me just illustrate one in the geometry domain. So this is a simple one-step problem, but the problems got more complex multi-step problems. And this is the peer practice or testing condition where students have to generate, in this case they're trying to find this arc BFD given this other arc here. And then in both conditions, they also have to explain. So there's some self-explanation where they make reference to this glossary to indicate why the result that they produce is the right result. And of course, the tutor provides feedback on both of these steps. In contrast, in the worked example condition, half of those steps are replaced with, here's how you do it. Study this. And again, self-explain. So and again, this condition had this glossary to do this. So that's a simple design, and the results actually show that the worked examples indeed improve both the efficiency of learning. Perhaps no surprise, it takes less time to study a worked example than to do a problem. And 20% less time is non-trivial. You can take Friday off, basically, right? Furthermore, they showed greater conceptual transfer in one of the 2 of the lab studies. There were classroom-level studies. They added a 3rd condition where they adaptively faded from examples to problems as students developed, as students showed that they could do the self-explanations on the examples, and those produced better long-term retention and transfer. So that was the geometry tutor studies. Similar studies were done in chemistry and in algebra, and saw similar results. Always a reduction in time, and sometimes an improvement on long-term retention tests. And we also did some theoretical work, and I hope to have time to tell you a little bit more about SimStudent, but SimStudent's a computational model of student learning. And what we found with SimStudent is if we give it both examples and problems, it learns more than if, for example, we just give it examples. And the problems are important. Well, the examples are important because they're the basis for the system to induce the patterns that they need to generalize across contexts. But those generalizations are often overgeneral, and that's the source for what we sometimes call misconceptions. So getting feedback from formative assessments or problems is important to prune those misconceptions. So going back to use CLE to explain what's going on, this is one of the theoretical tables in CLE that makes this alignment between different kinds of knowledge and different learning processes. So testing supports this memory phenomena, and it thus is going to help you learn facts. But because you need to induce rules to generalize them to new contexts, it's not going to be very good for that. So basically what's happening is most of the cognitive psychology studies have focused on fact content, whereas most of these ed psych studies on worked examples have focused on domains where some induction and refinement is required to learn generalizable skills. They're often in STEM kinds of domains. And here, you essentially get the opposite effect. And if we understand these different goals, we can understand the differences here. I could give other examples of the framework that contrast the next, like understanding and sense-making versus induction, if I had more time. But I hope you get the idea that we're seeing not only these content treatment interactions, if you will, but starting to develop some theory of when the treatment is going to be better for one content area but worse for another. So what should we do to scale practice here? Is this what we should do? Take our theories of learning and apply learning science to do instructional design and bring it out to practice and see if it works or hope that it works? I mean, we should at least do this. And, you know, apologies for those of you who wanted to answer all of the above for my assessment questions, but I wanted to force you a little bit here. I don't think this is enough. And one piece of evidence of this is the U.S. Department of Education in the last 10 or 15 years ago has spent millions of dollars on big randomized field trials. And about 10% of those have come back with positive results. And I think we need to do better than that. We need a scientific pipeline that has a hit rate that's higher than 10%. And I think one of the reasons why we don't have a higher hit rate is that the science has been somewhat ignoring these external validity issues about transfer. You know, and even as I think I already illustrated, if you probe these things a little bit more deeply, learning scientists, especially ones from different contributing disciplines, don't always agree on what's best. So we need to go beyond applying learning science, and we need to build infrastructures where we can all do learning science. We need to do data-driven, iterative engineering. Yes, start with the existing theories, build models of your learners and the desired expertise, use that to design instruction, but don't stop there. Collect data, interpret the data to gain insights, and redesign your models and your instruction and try again and see what happens. So we want to go through these loops of design and deploy, collect data, discover, design and deploy, and so forth. And we might also tell the world about our results and contribute to theories of learning along the way. So this kind of process is one that I think we can support through better social cyber infrastructures. And LearnLab was one of those, and in some sense lives on, but in fact our NSF funding is over. So what I want to say is, let's do this because every school and university should be a LearnLab, right? We should all be engaging in this process in our institutions, right? In that science paper, in addition to that complexity analysis I showed you, we gave 5 recommendations, and a number of them are along the lines of building such infrastructures. There's also this Global Learning Council report that has similar recommendations and elaborates how to get there. It's not just about doing the loop of continuous improvement, but we need university administrators that are going to foster a culture. They're going to change the incentives. We need to get credit, not just for the research we do, but for making improvement in our courses. So incentive structures need to change. And we should be drawing upon what's happening at other universities and contributing what we learn to other universities. So if you take a look at this document, you'll see 9 recommendations associated with these 3 areas. And you'd also, if you've made progress in any one of these areas, there's an opportunity to brag about what you've done here by entering a case study on this website. I'm going to give you 3 avenues for scaling practical learning research, and I just gave you one of them, which is make every school, every university a Learn Lab, where we foster a culture of iterative improvement, and we start sharing not just data, but assessments and analytics with each other. So the next topic here is to give you a sense for what one of the things we can do with this data, which is to do more deep content analytics. And if I had to put my money on, if you were going to do one thing to try to improve one of your courses, you should do cognitive task analysis. So actually somebody mentioned this in a question this morning. I think they were talking about how doctors don't know what they know. And this has been shown over and over again. Like if you know the old history of building expert systems, people building those systems thought, well, just ask experts what to do and codify it. But they found that they didn't know what they did, right? They can't articulate it very well. Richard Clark's done a great series of these cognitive task analysis and has articulated what he calls the 70% rule, which is basically that essentially 70% of what experts know is outside their conscious awareness. It's a tacit. It may be a consequence of automaticity that happens as a result of expertise. I actually think that it's largely a context of most of what we learn implicitly through imitation and through practice. But those are certainly 2 sources that lead to this phenomena. And one of my favorite studies of Clark and his team is one at a med school where, you know, those medical professors, they're smart people, and the students are smart students, right? And those courses work. But do they work as well as they could? Well, if they're only drawing on 30% of their conscious expertise, you might imagine that those courses miss teaching some things that are important. And sure enough, when Clark interviews multiple, he does this structured interview approach to cognitive task analysis. They interview multiple experts. They keep probing them and probing them. How would you do this? What if the trauma is different in that situation? Do you go to a different location to insert the catheter? You know, what's the exact angle at which you insert the needle and so forth? They really elaborate that, and they produce a brand new course, quite to the surprise of the instructors who didn't realize what they essentially knew. What's also neat about this course, we were talking about transfer in an earlier session. Not only did they do some paper-based post-assessments, but they followed these young surgeons out into the field and, for example, counted how many times they had to reinsert the needle while doing catheter insertion. And the students who had been in the CTA-based instruction were much less likely to do a second insertion or a third insertion of the needle. They had other field measures, but that one somehow makes your skin crawl a little bit, doesn't it? Powerful. So that's a very qualitative approach to cognitive task analysis, but what I want to suggest is that we should do that. It's really powerful and insightful, but it is also costly in time and effort. I want to suggest that using data from our online systems, we can do a more quantitative approach to cognitive task analysis. And so the key idea here is that if you've got a good characterization of the latent skills and concepts that you want students to acquire, in other words, if you have a good cognitive model of the domain, then when you organize data in terms of that cognitive model, you should see a smooth learning curve. So let me try to elaborate what I mean by that. So one kind of learning curve is to graph the average error rate of students as you see them get successive opportunities to exercise some area of competence that you're after. And so, you know, what do you want to see? You want to see the error rate go down with successive opportunities. And I'm going to show you data from a geometry cognitive tutor. And I guess what I want to emphasize is these opportunities have 2 meanings. They're assessments, but then there are also learning opportunities because students get feedback from the tutor if they get it wrong. So here's a learning curve, or maybe not. If we organize the data just by sequencing every task the students did in the order that they did them, And that's not a smooth learning curve, right? There's something wrong with the idea that when I do geometry, I get better at geometry. It's not that simple, right? We need a finer-grained cognitive model, and the bumpiness of this curve suggests that. This is a curve out of Datashop, and it's with a model that only has one component to characterize all the different tasks in the domain. And you might imagine that this blip is going up because the topics are changing, right? Now, this is trapezoid area for the first time. So if you code this exact same data with a finer-grained set of skills, or what we call knowledge components, and reorganize them so the first opportunity at trapezoid is not here, but here, now you get a smooth learning curve, and you have some data that suggests that this more elaborate cognitive model is better than this simple one. This is an extreme example, and in some ways, not very interesting, although there are proponents of faculty theories of transfer that might suggest that you should see a learning curve here. But the upshot is this distinction between this rough curve and this smooth curve can be used to evaluate models. And we can do that here. I'm sort of doing it visually, but this blue line here is a statistical model. It's basically a logistic regression where we're predicting the log odds of correctness for each student on each step in each problem, using a model of what skills or knowledge components each step requires. And basically, these other parameters here are the student's general proficiency, which if you know item response theory, you might recognize that. For each of the skills, essentially how hard or easy they are initially. And then here's the curve part. This says for each opportunity to practice, what's the gain in log odds in the relevant skills. And so we can fit these models to these data and then use them to compare. When we change the cognitive model, we are essentially changing this Q matrix. We can see which one works better, essentially. And when we look at individual curves, so of the 12 components I mentioned earlier, a lot of those individual curves look pretty decent. This is not the biggest sample. It's about 60 students here. But some of the curves are flat, and those are opportunities for improvement. And if we drill down and look at all the tasks that are labeled with this component, this is another visualization tool. These are error rates on those. Some are really easy and some are really hard. There must be something about the cognitive demands of these that's different from those. And even though originally they were all coded as though they involved the same skills, that's got to be wrong, and that's probably why this curve is flat, that they're doing harder things out here when the error rate blips up. So we can try to interpret what's going on by inspecting these harder steps and problems and comparing them to the easier ones. So to give you a sense of this, here's of 5 different cases where originally has the same skill label. The first one's hard, these 2 are easy, and this one's medium. And what ends up apparently explaining this is in some of these problems, these are all problems where students have to not just apply a formula, but combine 2 formulas to find the area of an irregular shape. Well, doing that is particularly hard when you're asked to do it without any prompting. In contrast, when you're given prompts to find the area of the square versus find the area of the circle, that is of medium difficulty. And if you're given new values for the same problem, that's much easier because the plan was already formulated here, and they're just essentially doing arithmetic here. So if we take that same data, the original model's predictions are here. They're flat because there's only one skill component, whereas here we see 3 different, essentially 3 different skill components fitting the data much better. And the important thing here isn't so much that we get a better prediction fit. The important thing is that we can interpret these results to redesign the course and go around this loop. We can make a discovery about how we weren't giving students enough practice at this key planning skill that is involved in more novel problems where they can't just pull one formula off the shelf and apply it. So what did we do? Well, the thing that turned out, we actually made a number of changes based on this insight to the system, but the one that was most powerful is that we developed some activities to isolate this planning step And in fact, we didn't do super sophisticated forms of interaction. We actually just used a simple kind of multiple choice question, but the idea was to have them say what their plan is without executing it, and that we could focus practice just on that critical planning step that our analysis suggests was the real difference between those hard problems and the easier problems. And when we do that, we increase the amount of time they spend on these planning composition steps in the treatment group. We end up decreasing the sort of busy work that they're doing on the individual formulas that they're mastering more quickly, overall reducing the time by 25%. And again, that's important. Like, that's 3 years of college instead of 4, if you could scale that. Right? Which do you want to pay for? And importantly, they actually, no surprise, are better at those planning problems on a post-assessment. So we get both wins in terms of efficiency and in terms of effectiveness. And this is really more than just saying students learn what they spend time on, because as a matter of fact, the control condition spends more overall time on problems involving combining formulas. They're just spending a lot of that time on aspects of those problems that don't involve the difficult cognitive skills. That's what we have to help students acquire. We have to create contexts in which crucial decisions to act are being made. And we have to understand through the cognitive task analysis what are those points where crucial decisions are being made. As a side point, I think I'm all for sophisticated technology, but I would pick a really well-engineered multiple choice activity over a sort of off-the-cuff, let's just have them do a task, right? Even if it's very open-ended. That's a data-driven approach to doing deep analysis. Another approach is a more theoretical approach, and this was the sim student idea I mentioned. And there is a longer literature on originally called pseudo-students on modeling student learning. In the earlier literature went after this idea of a kind of crash test to evaluate course changes through these simulated students. But another thing you can do is this kind of generation of better cognitive models. To set up what this does, I think I'm running low on time, but here's 4 different problems in algebra, and I wonder if they all look the same to you, or does any of these look particularly hard? Maybe the last one? Yeah. The second one? Yeah. Well, the second one has the X on the right side, so that might be a difficulty factor. So SimStudent makes a prediction about this, and I don't have time to go into the details, but SimStudent learns skills. It has 3 learning mechanisms, essentially to learn where, when, and how to learn these skills. It does induction from examples and gets feedback by doing. Here's a video of SimStudent being taught equation solving. And at first you show it a problem, and SimStudent says, well, I don't know how to do that. Show me. And I'm stuck. And you show SimStudent here divide both sides by 2. And it learns from that a production rule using those 3 mechanisms. And it's building it on a representation of the domain. Then it'll go to a next problem and start, well, it needs more demonstrations on this first problem because it's never seen these problems before. But when you go to the next problem, it then starts doing things itself. So here, what's it going to divide by? Any guesses? -3 would be good, but it actually thought the generalization was to pick the number, so it says divide 3. So kind of things students do, right? They don't quite get the induction right, but the negative feedback then helps SimStudent refine that induced skill. I also have a video here of SimStudent learning fraction addition, which I won't go through, but this one's pretty cool because it shows a whole unit of instruction, and after a lot of instruction, SimStudent's really good at doing it. Has had a number of demonstrations and a number of negative examples along the way. A fourth mechanism that it uses is a representation learning mechanism that Nan Lee developed as part of her thesis, and it has this nice paper in the Artificial Intelligence Journal. And she demonstrates that with this combined with the skill learning, she can show that better representation learning leads to better skill learning, and furthermore generates cognitive models of human students that more accurately fit the data than human-generated models in 3 out of 4 cases here across different domains. And in particular, going back to this example, SimStudent does okay in transferring across these three contexts, but this is the one it finds particularly problematic. That's because there's no number in front of the X. The error rate is twice as big there in the human data. So SimStudent got it right in that regard. And this is not yet another instance of cognitive task analysis, but this time it was theoretically generated and then confirmed with the data. So that's scale deep content analytics. I'm running out of time, but fortunately the last point is really the topic of my LAC talk, which is about scaling iterative course improvement. And last year at this conference, we presented this Learning is Not a Spectator Sport and did this causal analysis of how different activities students engage in correlate with their outcomes, and showed that learning by doing is 6 times more powerful in predicting their outcomes than learning by watching. So do those results generalize, and are they causal? Come on Friday to our talk and find out more about that. So I think there's a pathway there to do these process to outcome and analytics and do it across courses. So one nice thing about I know these are correlational results and we need to do the experiments, but you end up doing a costly experiment in one domain. The nice thing about these kinds of found data analytics is you can do them across many domains, and you can start to get a sense for generality. So you sacrifice a little on internal validity, but gain external validity, and I think that trade-off's worth exploring more. To summarize, I have argued that you cannot see learning, that you should be aware of illusions both as students and as instructors. We need to use data to break those illusions. Students need feedback on their progress, need formative assessment, need long-term assessments, and instructors need these data too. I articulated 2 big challenges for us: the domain-specific challenge that's answered by cognitive task analysis, and the promise that maybe our data from these systems can provide another way in addition to more qualitative forms of cognitive task analysis, to do quantitative task analysis, and articulated how we need to do a lot more of this A/B testing across courses because we need to better understand these content treatment interactions in this huge design space. And finally, I do think the opportunities are huge here. We can I think we can make these courses not only more widely accessible and more personalized, but much more effective if we can build a social technical infrastructure at all our schools and universities where iterative improvement can be done. Data is great, but use it to iterate and improve your designs and bring it forward. So finally, thank you very much. Here are some of the places you can go to find out more about what we're doing, and another picture of my girls to remind us what's really important. Thank you very much. So as we go into the question period, if you could do the post survey, that'd be wonderful. It's a different URL, but essentially the same set of questions.
I'm Joseph Williams from Harvard. You mentioned a lot of things in your talk about iterative improvement, and maybe it's changing the culture and sharing data and assessments, and I think people are focusing on that a lot. You also mentioned the experiments that you're able to do with that $47 million. And I'm wondering, to get a kind of Learn Lab on the cheap, would it at all work to actually focus a bit more microscopic in terms of, what if we just were to build better technology of experimentation? for randomized experimentation. So what if we said, you know what, everyone needs to just start organizing their collaborations around randomized experiments. You ask an instructor, which part of your MOOC, is it the explanations, the problems, the work examples, are you open to improvement? You suggest your visions, and we suggest ours.
Yep.
And then when we run these, we don't just run experiments the way, you know, I used to as a psychologist, and then report the results. But we actually build it the way Google does, where you can actually use algorithms to, if something's working, you start putting it into practice.
Yeah, I totally agree, and that's consistent with the idea that to get this to work, we need a social technical infrastructure, right? And one of the features of a technical infrastructure is that it's easier to construct A/B tests. And yeah, you know, there are some great examples, especially in the educational game space, of like Derek Lomas did. There was something like 7,000 different conditions in one of his studies, just by varying features of his game along multiple dimensions. So it was like a 7x2x4x3x2 design. But he gets 10,000 kids a day to play this game. So you can do those huge kinds of studies. So yeah, that's a case, like Mike said, where scale can allow us to do something we couldn't ever do before. And I agree, just even randomization of features for which we don't know what's going on is a form of experiment that we could be doing more effectively. Yeah, you know, and sometimes people worry about ethics there, and that's important to worry about, but we're really doing experiments on learning all the time, right? It's just that we're not comparing them to each other, right? And there are different instructors running different experiments with different outcomes.
So thank you for the talk, and I actually find your point that there are many illusions about learning very interesting at some level. Fascinating that we have those illusions. You said breaking them is very important, and in order to do that, we should do learning science. But I would argue there are only so many learning scientists in the world. So how can we have more learning scientists, and is there a way in which every practitioner could be a learning scientist and do learning science in their own Learn Lab?
Yeah, well, I think that instructors already look at data, right, when they're formulating their grades. Well, so yeah, they're not necessarily looking at pre-post results because they're not giving pre-tests. So part of that is indeed to change the culture so they have better data to make inferences from. But you know, especially at the university level, where most of our instructors are scientists, it should be okay for them to engage in a little data analysis and a little experimentation. Indeed, there's some learning hump that they need to get over, but most of our universities have teaching centers, right, that could be supporting faculty in learning how to apply these methods to their courses and get better. And as much as I want to impact K-12 instruction, maybe what we need is to be a model for what K-12 instruction should be by doing it ourselves in our own courses.
This is a great talk, but I feel a little bit depressed by the whole story here, because it sounds like you basically said we have to just keep trying things in all kinds of different contexts with different variables in different situations. And so I'm wondering whether you think there's at some point going to be 3 or 5 or 7 kind of principles that you could extract from 400,000 different experiments. I guess one of the reasons I'm thinking that way is that if you want to give somebody advice, or you want to have some sort of predicted theory for someone who's doing something in practice, you know, a 470 variable kind of model is not as intuitive and is going to be as useful as something that boils it down. So are there some big questions we could aim for, and will we ever get there? Yeah,
definitely. And you know, that's why I was trying to, the CLE framework and the idea of reasoning through a set of what are these instructional principles function to do in terms of what learning processes they affect, and then what do those learning processes do with respect to what they function to help us learn, you know, whether they're facts or skills or principles. And that theory is going to be, they're going to be meta principles. They're essentially the same principles, but to use one thing that Herb Simon always said, it's more about the if part than the then part, right? It's not so much do this. It's if, under these circumstances, right, if your focus is on principles, then do accountable talk. But if your focus is on learning vocabulary of a second language, then do optimized scheduling and don't do accountable talk. Those are principles, but they're not the kind we're currently producing because we tend to leave those conditions off. And we do because we don't have the scientific basis to accurately produce them just yet. And there's theory work we need to do on that score. So I don't mean to be depressing here. But you know, if you look at the A/B testing literature more generally, it is the case that even there with simpler HCI things, we often get it wrong, right? Those A/B tests are often surprising. So I think, you know, that's the idea that we need this iterative engineering process on top of the science. The science has to get better, but we need to check whether the science is working in our particular context. And I don't think that's that hard to do. I think it's going to take time for our infrastructures to change, but I think we can do it.
So I have a quick short follow-up and then Danielle. So I'm confused, which may be good for learning if I'm to self-assess. Because you started from theory, but my sense is once we build this distributed learn labs everywhere, we're moving more into the case study world, where I'll just do iterative, like all design-based research, or I'll just improve what I do, and then I can say that it works in this case, and then it's kind of death of theory in favor of data. So what's missing to, like, I think that something is missing to bring it back. Is it, or am I wrong?
Yes. No, the interaction has to be there, and you know, you can get a long way with data and with experimentation, but I'm a firm believer that if you don't have interpretation, you don't have a deeper understanding of you know, what your analytics are about and what they're telling you, you're not only, I mean, it's not just about understanding, but it's about being actionable, right? You have to understand what those models are doing. So even in the sort of local iterative changes, I think, you know, these learning centers are going to need to help people think about how to interpret that data and use those interpretations to make change. So theory is relevant there. We're not going to get away from it. It's not just data.
Well, you know, I was about to say much the same thing, but from a more positive point of view, just a compliment you can, because there are people who are doing, and I won't name names, meta-analyses and reviews of the literature indicating what is good and what is bad. And one problem with that is that it is not theoretically driven. And so if you don't have a good theory of learning and a good theory and expand that learning from not only the learning of facts or memory to comprehension and problem solving and deeper learning, right, you're going to come up with answers that are very simplistic and won't generalize. And to the extent that we do that, we're going to confuse the educational practitioners by saying, for example, you know, testing effects, they're the answer to everything.
Right.
And there's most certainly not. Right. We need to take into account what the type of learning is and what and have a theory as a basis. That theory may be wrong, but
right.
I just compliment that your approach did start with a theory and expands from there.
Yes, thanks. I guess one quick comment on that is, I mean, I think these meta-analyses are useful, and it is interesting how, you know, most of them give us the average effect size, but if you look at the distribution, there's a lot of negative results on every one of these principles, right? And we need to be more conditionalized about understanding why, you know, yeah, there's random variation as part of that, but sometimes it's because of these mismatches, right? And yeah, let's dig in on those.
So I'm a very big fan of this work and this talk. I had a question about it in terms of one comment you made is that universities should have practitioners. A lot of content presented at a university level is vague, it's ill-defined. It actually has a lot in common with a presentation like this where if you ask me what are the learning objectives of this presentation, I kind of say, well, gosh, I want people to understand what learning engineering is. But I have a really hard time actually struggling to do that. If I go from there to what is the cognitive task analysis I would need to do on a presentation like this, that becomes very hard. That's true of many graduate level courses especially. I'm wondering if you talk a little bit about whether you see this applying in contexts like that, where it's the material's a little ill-defined, what students are learning is ill-defined, or whether it's a different set of techniques or just go to a little bit more depth there, and whether it's economical to do there.
Well, yeah, I think that's a very important question. One, certainly not the only strategy, but one strategy for making progress on those ill-defined domains is to try to define them better, right? And that's basically what cognitive task analysis is about, to understand what are the consistent and reliable ways to generalize, say, interface design, right, is one of those.
I was wondering about things like here where the research was from 2014, so it just said it hasn't been enough years where it's, you know. I was wondering about things like this, where, for example, the research here, you had sites from the past 5 years, where it's just a very new thing that's being taught. That's what differentiates university instruction from K to 12. And by the time having that be well-defined, the field has moved on in many cases. It does become well-defined, but that moves it to undergraduate high school courses.
Yeah, well, I think we do want to get to the point, and I think we're close to, you know, we can have a pretty good first shot at a course, right? And if it's only going to be taught for a couple semesters and it changes, then that's the best we can do. But I don't actually think that really happens. It may be that new content gets changed somewhat, right? And we might eliminate some of it, we might enhance some of it. We might actually start teaching it to younger students because they can get it, right? So I do think there's opportunities to iterate there. But, you know, we definitely should continue to do new stuff, and when you have to use your intuition, right? Yeah, so this is the pre. Thanks, Jim. Let's see. The post should be at this other tab. And let's see. Responses, 58. Come on, folks. Where's the rest of you? As you listen, I don't know when we're learning. That flipped. Excellent. This one remained the same and consistent with my answer. This one flipped. Nice. Oh, apply is even lower than follow your intuitions. Interesting. By the way, I think all of these are right. Like, you'd never give up on your intuitions, but you need to, and this one was already right, basically, but even more so. Good job. Nice.
Please join me in thanking Koedinger. So thank you very much. I asked the learning analytics people to please be patient a little bit and help us conclude the successful learning at scale. And first I'll invite Justin, I saw you here, to tell us a little bit about next year's learning at scale.
Great, thank you so much, Ido. I just want to invite you all next year to Learning at Scale 2017, which will be held at MIT. Claudia Urea of One Laptop Per Child has agreed to be the general chair. Candace Till from Stanford and I will be the program chairs. We haven't exactly settled on dates yet, or format, or anything else other than the fact that it will be at MIT, which gives us a wonderful opportunity to reshape the conference for next year. So I'll be around this evening at the reception and the rest of the week, and if people have suggestions about new directions for the conference, I'd be delighted to chat with any of you. And certainly very grateful to Piotr and this year's program chairs and other folks who helped us continue to experiment and iterate and all of those kinds of things. So looking forward to seeing many of you, both from Learning at Scale and hopefully from LAC next year at MIT. Thanks.
Thanks. And so yeah, we hope to see everyone from whatever community over there. And next, so the learning analytics people get a glimpse of what you've missed over the last 2 days. Best papers of learning at scale. Vincent?
So thank you. So first of all, it was a really good conference. So we started, yesterday Ido started with asking you to turn to the person next to you whom you didn't know and introduce yourselves. That was yesterday, really. If that hadn't been such a pandemonium, I would now ask you to turn to somebody and just thank them for their contributions, because I thought everybody of you really contributed to this conference, and not in the least the people who submitted papers of the various kinds that we invited. And we thought it would be appropriate to give a few of you, although the quality was uniformly high, we thought it would be appropriate to give a few of you a moment in the sun. So we would like to announce a Best Paper Award and 3 honorable mentions in the tradition of other conferences. Just to show you that we approached this task with great seriousness, we had criteria for deciding which papers were especially good, such as innovation, so papers that are particularly original, of course, potential impact on research and practice of learning at scale. Across the papers, we wanted to have some diversity in the topic and the methodology. Research, of course, had to be sound, and we were also looking just for papers that had a certain spark, that spoke to us directly, to our heart as researchers. And so what we did was we looked at the papers that got the highest marks from the reviewers, so a small number of them, a subset of all the papers. Then we as program co-chairs, so Ido, Judy, and I, read those papers very thoroughly. We looked at our own criteria. We then fought hard, but eventually reached consensus, and so we decided according to those criteria. So, what papers were especially good? So we had 3 honorable mentions, and here are the 3 honorable mentions. Learning transfer, does it take place in MOOCs? An investigation into the uptake of functional programming in practice by Chen, Davis, Hauff, and Huben. Axis, generating explanations at scale with learner sourcing and machine learning. Williams, Kim, Rafferty, Maldonado, Gaius, Lasecki, and Heffernan. And the 3rd honorable mention is using multiple accounts for harvesting solutions in MOOCs by Rupieres, Valiente, Alexandron, Chin, and Pritchard. So please, a hand of applause. Now, sometimes it happens to me in my role as the director of undergrad programs that students who applied to be admitted to our 2nd major in HCI are disappointed that they couldn't get in because the capacity is limited. And one of the things I tell them is, it doesn't mean you're not a good student. It just means there is this incredible demand, and so you might be really good. So if your paper wasn't among those mentioned, it doesn't mean it wasn't a good paper. I thought all papers were great. But the one that we like best is the civic mission of MOOCs, measuring engagement across political differences in forums by Reich, Stewart, Mavon, and Tingley. So the best paper. And of course, if you win the best paper, then you have to organize next year's conference. I have a couple of other topics, so before we close. The International Journal of AI in Education, which is an interdisciplinary journal that publishes work on advanced learning technologies that is highly interdisciplinary, so it publishes both work on technology and empirical studies. This journal is planning to do a special issue that'll be on learning at scale. So Ido Roll and Dan Russell have kindly volunteered to be the special issue editors. So I hope you will submit your good work to this journal. This journal, in fact, accepts papers that have been previously published as conference papers as long as there is 30% of new content. So the things that you didn't have space to include in your papers or the things that you now, by interacting at this conference with your peers, have thought of, oh, I need to do this additional analysis. If you add those and submit your paper, I think this will be a great special issue. So I hope you'll submit. Finally, we'd like to get your feedback on how this conference went so that it can be even better next time. So Ido has put together an exit survey. You'll be receiving email about this survey with a URL. So this is not the survey that Ken just did. It's about how the conference went. So please, when you get this email, really take a moment. We really value your input, and we'll definitely take that into account the next time we organize this conference. Thank you.
Okay, I don't want to stand between you and the evening's entertainment. So just very briefly, a close from me. Thank you all for coming to Learning at Scale 2016 in Edinburgh. We hope that you've enjoyed the conference. We hope that you've arranged the multi-seasonal weather that we organised today, especially for those who went and climbed the mountain in the snow. That was really good. We've loved having you here. You've been no trouble at all. You've been amazingly well behaved, which was really nice to see. All of the conference sessions have been recorded and have been streamed. The recordings for them will all be available on the conference website as of next week. So we want a day or two off to assign them all and get them up there. So everything will be there by next week. If you have tickets for the reception afterwards, that's this little orange thing that says drinks voucher. It is drinks and food. That takes place out in the central area at 6 o'clock. If instead, and probably when we close, if instead you've decided to head for the bright lights of Edinburgh for a wild evening out, then you should head to Rose Street, bus or taxi towards Rose Street. The old bars, experts are nodding at me. The old bars, the places to eat, are all down there in the centre of town. For those of you who are staying on for LAC 2016, then Dragan Gasovic and the team will take over from here, and I hope you enjoy that. For those of you who are heading for home,